Similarly, let's solve another very interesting problem. This is a rod and this is hung from the ceiling. There is a ring here. That ring is tied to a string going round through the pulley, and mass is hung from the other end of the string, m. This angle at present is given as 60 degrees. The velocity of m, suppose, is given as v meter per second downward. Now at this very instant it is asked what will be the velocity of this constrained ring. The ring is constrained to go through the rod. The ring will only have a horizontal velocity, and at this very instant what will be the velocity of this ring? It's a very interesting problem and pretty much the same as we did before, but this time you should really try your hand on this and you should really work this one out. So again, what you have to do is you have to write the constraint relation. Every time you have to do that. And again, a natural choice would be making this triangle, because wherever the ring goes, this distance b is going to remain constant. Even if it comes here, this distance b is going to remain constant, because these two are non-moving ends. This distance b is going to remain constant. So let's call this as x again, this as y. Again the relation would be y squared minus x squared is going to be b squared. 2y dy by dt minus 2x dx by dt is equal to 0. We have exact the same relation, and you can see this final relation will also is going to come out as same. Now dy by dt, you have to appreciate again that dy by dt is actually v, because if this mass comes down by a distance of dy, then there has to be decrement in the length by the same amount dy in the hypotenuse of this triangle, because the length of the string is constant. If string increases dy in this direction, then certain amount, by the same amount dy, the string has to reduce in this direction. Fine, because the length of the string is same, constant. So dy by dt is actually v. So we have 2y into v minus 2x into u. Suppose the velocity of this we are taking as u, then dx by dt is of course u. That is 0. U will come here, out from here as v upon cos theta again. Cos theta, theta is given as 60 degrees, cos theta will be half. So your velocity is going to be twice as the given velocity. Okay? Okay, let's do another one, and you'll see more in all the question you have to do the same thing. Write the constraint relation and then do the differentiation. Do some manipulation here and there, and you'll get the required relation you are looking for. In the question it is given that this distance is b and this distance is b as well. And it is given that this end of the string is coming down with velocity v. Now it is asked that if the distance of the center of the pulley from the top is x, then they are not asking for any instantaneous speed, they are asking the speed of this mass m as a function of x. Fine. So as the x is going to decrease or increase, the velocity will be changing for m. So they're asking what is the velocity of mass m as a function of x if the velocity of this end is going to remain constant as v. Okay, so there's nothing new in this. You have to do the same thing again. Write the constraint relation, do the differentiation, and get whatever you're looking for. So do it, please. Okay, so how are you going to write the constraint equation in this? What thing is going to remain constant and what is going to change? If you go in this triangle, if you consider this as y and you write the constraint relation as y squared minus x squared is equal to b squared, then that would be wrong actually. You shouldn't use this constraint relation, because you don't know when this is going to up, that symmetry may break and this b may not be b, that may change. So you are assuming that b is going to be constant. That may not be the case. That may be the case, may not be the case, I'm not sure, and neither would you be. So what we should do is we should look for a better constraint relation. Whenever you can make the length of the string constant, you should always go for that kind of constraint. The length of the string should remain constant. And even if you, you can go with this as well, but that will unnecessarily complicate things. For the reason, you know why? Because it will be difficult to relate this velocity with dy by dt. If you take rather this relation, suppose you take this as y and this is given as x, then if you take this y, then dy by dt will straight away v, and dx by dt will be your required velocity of pulley. So taking this as y is a better idea. You can go with that as well, but that will be a little complicated. This will be straightforward. Now let's write the constraint relation. The length of the string has to remain constant. This length is root over b squared plus x squared. 2 times this will cover this length, and this length is y. This is going to remain constant. This is the length of the string. Now this is the constraint relation which is better than before. The reason why, because when you differentiate this, any problem in differentiating this function? The differentiation of this is 1 upon 2 root over b squared plus x squared into 2x into dx by dt plus dy by dt is equal to 0. This is the differentiation. Now from here we'll see that dx by dt is the required velocity and dy by dt is the given velocity. Because this is y, dy by dt is actually the rate of change of this position. So dy by dt is the given velocity. If you take this as y, then dy by dt is not the given velocity. Okay? Okay, so that's the benefit of taking this constraint relation. Okay, then from here the story is well known to you, the path is well known to you. You make this 2x upon b squared plus x squared, dx by dt is the required velocity u, and this is the given velocity minus v. So u from here straightforward you can see as root over b squared plus x squared upon 2x into v. This is the required relation between u and v. Fine. So the job is pretty easy, but as you have learned here how to make the constraint relation, that is important. Or you can, what you do here, you take this as y and take this as x, and you again work out. That won't be very difficult. You should try this at initial stage of your learning, and then you see how to relate the dy by dt in this case with the velocity v, and you should still get the same answer. You should still get the same relation. So I highly encourage you go with this y and this x and try to find the relation between the velocity of pulley and this given velocity with by writing the same constraint relationship. Okay, so it will be a good exercise for you, and you should really go for it. You should really explore different ways of doing it, different methods of doing it, so that you are never stuck at any point. There's always a solution. Some solution would be simpler, some would be a little more complicated, but there's always a way of working out whichever way you go.